Hello everyone, welcome back. This is question 3, so the final question of the 2019 Mechanical Systems Physics exam. So this question is focused on simple harmonic motion, which I believe is the hardest part of mechanics at level 3 because it's not really assessed at level 2, so I will try my best to explain everything quite in depth. So question 3, it looks like we've got the pendulum system, so a swing. So J is enjoy a swing at the playground. We've got the period of one oscillation is 2.40, so that's the time period. I'll just write that down. And J maintains a constant amplitude, so that's also another bit of information we can use. 0.3. By swinging her legs back and forth to replace the energy lost due to friction. The mass of the system is 70 kgs, so we've also got the mass. And J's motion can be considered simple harmonic motion. Calculate the maximum velocity of J and the swing. Okay, so the maximum velocity, so remember, this is not angular velocity, it's just linear. So V equals the amplitude times the angular velocity. So this is not on your formula sheet, so it's a formula that you're going to have to remember. So I'll just make that clear. But there are some questions where you can, some equations where you can sort of get it from. You just have to do a little bit of algebra work. So we've already got the amplitude, but we don't have the angular velocity. But we know on the formula sheet that the angular velocity is 2 pi frequency. However, we don't have this either. But if we're smart, we can recognize that the frequency also equals 1 over the time period. And we do have the time period, which is 2.4 seconds. So we can plug this in place of F. So it's going to look like this. 2 pi over t. The 1 on the top just cancels out because it's 1. So that's the equation for angular velocity. And we're going to take this and we're going to plug it instead of the W. So we're going to get V equals the amplitude of 0.310 times 2 pi over 2.40. And that should give you an answer. Let me put on my calculator. Of something like 0.811 da 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 da. So we're going to round it to 3 significant figures from this figure here. 0.812 meters per second. That's question A done. And this is worth and achieved with the correct working. Right. Now this one, I thought this was an excellence question, but it's actually only worth a merit. I'd say this is one of the toughest merit questions I've seen. So we are asked to use a reference circle or another method to determine how much time J's displacement is greater than 0.2 meters from equilibrium over one period. So we are going to use a reference circle to start this. So if we draw our reference circle, okay, now we need to know how much time his displacement is above 0.2 meters from the equilibrium. So if I sort of draw it out like this, right, we know that the amplitude is this height here, right? If I just draw this, it's the same as this height here, so that's going to be 0.310. So we can roughly estimate 0.2 meters is going to be maybe around this tall. Okay, I'll just sort of do that. And that's also down here as well. Okay, that's also another 0.2. So we need to find the time in this section here and this section here, because these are the parts of the circle that are greater than 0.2. So to do this, we're going to need to draw a right angle triangle and find the angle. So I'll use a different color so it's really clear. Oh, so this here's my triangle. My right angle's there. Now, remember the amplitude just equals the radius, okay? I think that's key to know. The amplitude equals the radius. So this is going to be our amplitude. This height here is going to be the 0.2. And we don't know what that height is, that length is, but we don't need to find it. It doesn't matter. So I'm going to redraw my triangle out here so it's more clear. Okay, so we're trying to find, we're trying to find this angle here, by the way. Okay, so here. Right, this is my amplitude because that's the radius, or you can call it R. This is 0.200. So using our trigonometric knowledge, we know this is the hypotenuse, this is the opposite, and this is the adjacent. So from our toa, we don't have the opposite, can't use that, and we don't have the opposite for toa, so this is the one we use. So cosine, so the angle equals cos -1 a over h, which is going to equal 0.200 over 0.310, and put that into my calculator. You should get an answer of 0.87 radians. Remember, we're not working in degrees. So that's the, oh, we don't need that. That's the angle where it is traveling greater than 0.2 meters from the equilibrium. So now we can use that to find the time. So the equation to find the time is just this equation here. We still need to find the angular velocity, so we can quickly find that with the information we found here. So 2 pi over t. So that's going to equal 2 pi over our time period, which was 2.40. And that's going to equal 2.62. I have just rounded that. So we can rearrange this equation. T equals the angle over the angular velocity. Now remember this, we want to find the whole circle, so we actually have to multiply our angle by 4 because we only found the angle for a quarter of the circle, but we obviously want to take in consideration all 4 parts, right? So our final value is going to be 0.870 times 4 divided by 2.62. And that should give you an answer of 1.33 rounded to 3 significant figures. Oh, that was a challenging merit question. So obviously if you got the correct time value, you will get a merit. If you correctly find the angle or the angular velocity, I think it's an achieve. So this, just this here, or the correctly found angle. Okay. J stops swinging her legs when the swing is at its maximum displacement. On the grid below, sketch a graph of her displacement over the next 3 periods. Include values for the time and for the initial displacement at t equals 0. Right, when t equals 0, it's just going to be her amplitude, so her displacement is going to equal her amplitude. Y equals a at t equals 0. So her amplitude was 0.310. So I'm going to put that roughly here, okay? And 0.310, that's A. And also negative amplitude, so negative 0.310, the opposite side. Okay, so now we've got our two amplitude values. So remember, we still have to. So another thing that you need to consider is that the time period is constant. So we want to start our graph from the max displacement. So I'm actually just going to draw a guided dot line to make sure that my waves will get smaller and smaller. So roughly like this, it will look like this. Right, there's my 3 cycles. Okay, so 1, 2, 3. Right, there's my 3 time periods. So we do have to label them. So this section here is going to be your 2.4 seconds, and remember the time period's the same, so that's going to carry on. This is going to become 4.8, and this is going to be 7.2. It goes up by 2.4 every single time, so increases by 2.4. Now you will also notice that the amplitude gradually decreases, and that's because she is losing energy, right, as time goes on. So you'll notice that the amplitude, it's still oscillating, but the amplitude decreases. So decaying, as we call it. Right, that's all you need. So this is a merit question. For merit, you needed to have the correctly damped shape. Damped just means this here. For 3 complete cycles with a constant time period and the correct starting maximum, and with at least one value of the axis. So pretty much everything I've done is a merit. Let's call that. Achieved as correct starting max and shape showing decay. So just the graph in general without like anything else isn't achieved. So graph shape. Or the correct time values and shape showing decay. So that's also something you can consider. Okay, final question. I'm going to go really quick because the time limit's about to run out, sorry. So you can read this. I'm not going to read it. I'm just going to pick out the main parts. So here's the mass. Here is the linear velocity. Here's the radius. So based off these 3 variables alone, that should sort of click to an equation. So what we're trying to do is we're trying to calculate the tension in the chain supporting the swing and the angle of the chain. So there's 2 things we have to do. Find the tension force and find the angle. Now you should recognize this as a right angle triangle, so I'm going to draw it out here. Okay. Your angle is up here, but we're not worried about that yet. Right, so this should really be important. So this will show you have to use some sort of Pythagoras theorem to find the tension force, which is this. This is your tension force. This here is your centripetal force because it's going towards the center, right? So it's your centripetal force. I can draw arrows to sort of help you. This is the weight force, right? Fg. Actually, I might just do this as a separate video because I'm not going to have enough time to cover it. Right, so I've done this whole question myself because the recording doesn't allow me to record over 15 minutes and there's only 50 seconds left, so sorry. You can just ask me in the comments on any part you're not aware about, but basically it's just your understanding of, Pythagoras theorem and trigonometry, basically, being able to recognize, I've written here, a squared plus b squared equals c squared. Your c squared is your tension force, which I've simplified here by square rooting the equation. Your a squared is your centripetal force, your b squared is your weight force. And then just using trigonometry, either formula works for the angle. I've tested both of them. They both give 59.4. So overall, this is an excellent question. I'm not going to show you where merit and achieved this because I don't have enough time. But yeah, that's it for 2019. I will upload more past papers from other years. Cheers.